In this video, we will continue our discussion on Chapter 2, and we will focus on periodic trends. As chemists, we like using the periodic table because the elements are organized in specific order, and we can get a lot of information from the periodic table. One of those types of information is periodic trends. And we will touch on a few of these, starting with atomic size and ending with electron affinity. And we will mention electronegativity in a few more chapters down the road. These are important to us because we can predict behavior of the elements based on some of these trends, and we can also explain why they occur, but we are not going to go into that much depth for this class. Also, remember that periodic trends are just that. They are trends. They are general rules, but there's always slight exceptions. So take it with a grain of salt. These are general rules, not hard rules, and so there are exceptions to these. Let's talk about atomic size. As the picture shows here, if we move from right to left in the periodic table, as we're looking at it, the atomic radius increases. And if we go from top to bottom in the periodic table, so down a group, the atomic radius, the atomic size increases. Now, I find it easier for some of these trends to memorize one thing, such as either cesium has the largest atomic size or helium has the smallest, and anything moving away from that atom is going, from helium, for example, is going to increase. So increase to the left of helium and increase down from helium. Or you can think of it as cesium having the largest, so anything going up away from cesium or to the right is going to decrease. It's up to you how you do this. Just make sure that you remember the proper trend. Let's take a look at a sample problem. In these types of problems, you typically will have a couple or even several different elements listed, and you would be asked to list them or order them in increasing atomic size or decreasing atomic size, etc. In this particular one, the question is asking you which one has the largest atomic size. So for A is aluminum or phosphorus. The first thing that we need to do is to get a periodic table and look at the placement of these elements in the periodic table. And here they are. Here's aluminum and here's phosphorus. Once you locate these, you can then recall what the trend is and then figure out which one has the largest, or in this case, the largest atomic size. Go ahead and try A and B. Moving on to the next trend, the metallic character. If you remember when we talked about the divisions of periodic table, we said that most of the elements in the periodic table that are shown in a slight greenish hue here are metals. We have this little, we call it stair step, or this little zigzag line over here. And those elements are shaded in kind of an orangey yellow color. Those are metalloids. And then to the top right-hand corner of the periodic table, we have the nonmetals. Obviously, the nonmetals and metals are opposite in character. So if I am looking at a metallic character and my metals are found, or my nonmetals are found in the top right-hand corner, If I move away from my nonmetals, metallic character is going to increase across the period. So if I am going from right to left, metallic character increases because I'm moving towards metals. Metallic character also increases if I'm going down a group from top to bottom. Let's look at another sample problem. We once again have pairs of elements, and you have to decide which one has the least metallic character. Once again, we pull up our periodic table and we find sodium and chlorine. So here's sodium and here's chlorine. So we need to decide which one of those has the least metallic character. Try A, B, and C. The next periodic trend we're going to talk about is ionization energy. Ionization energy is the energy that is required to remove one electron from a neutral atom. Basically, it tells us how hard or how easy it is to remove that first electron. If the ionization energy value is very high, that means that it requires a lot of energy to remove that electron, and vice versa if it is low. If you remember, once again, if you remember that helium has the highest value for ionization energy, meaning it is the hardest element from which to remove an electron, then anything else, so going from right to left, away from helium, or top to bottom, once again away from helium, is going to decrease in value. So the ionization energy is going to decrease, which means that it's going to be easier to remove the electrons, which makes sense if you stop and think about it. As we move down the periodic table, what are we doing? We are introducing new energy levels, and they get farther and farther from the nucleus. So for francium, for example, those outer electrons of francium are not really seeing the nucleus very much because they're so far away. And that really, what ties the electrons to the nucleus, or keeps them in the atom, are basically the attraction to the protons of the nucleus. But if those electrons are so far away, they don't feel that attraction as much as if we were closer. So the lithium electrons, for example. Think of it as you are trying to wave or trying to get the attention of somebody that is, and you're in a crowd in a football game, for example, and there's 50 people between you and the person you're trying to get the attention of. So it's much harder than if there are only two people in between you. Similar idea here for the electron being attracted to the protons. Let's look at a sample problem for each pair of elements. Once again, indicate, in this case, which one has the highest ionization energy. How hard is it to remove that electron from the element? Rubidium or lithium? Calcium or bromine? Once again, we go back to our periodic table, find where they are, and remember what the trend is. Remember that helium has the highest ionization energy, so anything moving to the left or going top to bottom is going to decrease. Why don't you go ahead and give it a try. And the last periodic trend we're going to talk about in chapter 2 is electron affinity. The electron affinity is the ability of an atom to attract an electron, to gain that electron. How easy it is for an element or an atom of an element to gain an electron. Now, if you think about if an atom loses an electron easily, it will not want that electron back, and vice versa. If they don't want to give up the electron, they will readily gain it. So those atoms that have high ionization energies, meaning it is very difficult for them to remove an electron, will also have high electron affinities, meaning they will gain that electron very easily. So atoms on the far right, so the nonmetals really, gain the electron the easiest. If you think about that, atoms in this group here are only one electron away from becoming noble gas configuration elements with full shells and 8 electrons around, or approximately, because they get more complicated as we go down. But they have full shells, and they're only one electron away from becoming noble gases. It is much easier for them to gain that electron, so they have high electron affinity, than to lose it. They have really high ionization energies. They don't want to lose electrons, but they want to gain them. So accepting the noble gases, because they do have a full shell, those elements in the far right, so group 7 or 17, depending on how you look at the periodic table. So the halogens have the highest electron affinities. Okay, let's look at the following pairs of elements and decide which element is easier to gain an electron. So how close are they to halogens? Lithium or oxygen? So here's lithium, oxygen. Aluminum is over here, or chlorine. Sulfur or calcium over here. So those two. Okay, go ahead and give it a try. And we will pick up the discussion on the last section of chapter 6 in the next, or chapter 2 in the next video.